Welcome to the Deep Dive, your shortcut to being well-informed. Imagine trying to simulate, say, how heat moves through a material, or maybe how air flows over a wing.
Or even how contaminants spread in groundwater.
Exactly. These things are governed by incredibly complex math, specifically partial differential equations, PDEs, and, well, for most real-world cases, you just can't solve them neatly on paper.
Right. Analytical solutions are pretty rare. So you have to go numerical. You basically discretize the problem, chop it up using methods like finite differences, finite elements.
And doing that, it transforms those continuous PDEs into something a computer can actually work with. These huge systems of linear equations, the classic REO-X B to a form.
Where A is this massive matrix for your system, X is what you're solving for, maybe temperatures or velocities at different points, and B is related to boundary conditions or sources.
And solving these matrix equations, one A get X equals B binder, efficiently, that's really fundamental to almost all scientific computing today, isn't it?
Oh, absolutely. It's often the main bottleneck. And today we're taking a deep dive into a really fascinating new way to approach this, based on the sources you shared, notes, timelines, paper excerpts from Nithin, Kumar, Goona, and Lama Tarsissi.
Yeah, this paper proposes something that kind of builds on a very classical method, but pulls in ideas from, well, fields you might not expect, like neural networks.
So our mission today is really to unpack the academic core here. We want to get into what makes it novel, how it works, how it performs, and critically, what this mix of old math and new AI concepts could mean.
Okay, let's get into it. The fundamental problem, solving $1 C.X equals BD efficiently, especially when A is massive from discretizing PDEs, the engine room for simulations, as you said.
And traditionally, you've got two main ways to tackle $1 X will be Babo. There are direct methods. Think Gaussian elimination, LU decomposition. They manipulate the matrix to get an exact solution.
Like carefully taking the equation apart to find X.
Pretty much. And then you have iterative methods. These don't go for the exact answer straight away. You start with a guess for X, and you repeatedly apply a rule to make the guess better and better.
Until you're close enough.
Exactly. And the classical Jacobi method is one of the oldest, simplest iterative approaches. It works by splitting matrix A into its diagonal D, lower triangle L, and upper triangle U.
Right.
Then each step uses that diagonal part D to update the guess based on the last guess and the B vector.
The old formula being 6K plus 1, D1, BL plus U, C.XK. That's a real cornerstone, right? Goes back decades.
Yeah.
Reference work by Varga in the 60s in the timeline.
It's foundational. But here's where Goona and Tarsissi get really creative. They didn't invent Jacobi, obviously, but they looked at that iteration and thought, can we rewrite this, open up something new?
Okay, so what's the key reformulation they came up with?
Well, first, they normalize the system. Divide A and B by the diagonal matrix D. So you get a new system. Let's call it BNAX, BRXDEM.
Where $Daniel is the love and Betty dollars is BAM.
Exactly. And the neat thing is the diagonal of this new Mertnell matrix is just the identity matrix I. So 1li plus ln plus un.
Okay, that simplifies things.
It does. And if you plug that back into the Jacobi formula, the normalized version becomes really quite simple. 6k plus 1 and I is C.XK plus Bn.
And they call alpha and I and beta B and all. So it's just sus_k plus 1 plus beta. That is clean.
Super clean. And this simple form is the launchpad for their higher order idea instead of just doing one step at a time.
They substitute the equation back into itself.
Precisely. So if you want 6(2) from 6 alpha kind of to x1 plus beta, alpha x0 plus beta, that simplifies to alpha 2x plus alpha plus I beta.
Okay.
And for 6, you substitute the 6(2) expression into the same logic, effectively doing two steps at once again. You end up with terms involving alpha 2 here.
So the power of alpha doubles each time. Alpha to alpha 2 to alpha 4, and so on.
Exactly that. By doing this recursively, they show that after care of these recursive substitutions, you get a solution, sex2k. It's equivalent to doing 2k or classical Jacobi steps. But you calculate it in one go using this formula. Sexy k 0 plus beta.
Where alpha k and beta k are these higher order coefficients.
Right, and they have their own recursive definitions based on the previous order. Alpha k1 to t n plus I do p k1.
Okay, wow. So you're doing potentially thousands, millions of iterations worth of work in one big calculation by pre-computing these alpha k and data things? An exponential reduction in the number of iterations. That sounds amazing.
It is amazing for iteration count. But, and this is a big but the paper highlights, there's a trade-off. Calculating alpha means squaring the previous alpha matrix LK. That's a matrix multiplication.
Which is computationally heavy, right? Much more so than the matrix vector multiplying classical Jacobi.
Way heavier. Multiplying two big square matrices is generally much more expensive, so you save iterations massively, but each higher order step involves calculating these coefficients, and that calculation is costly. You're front-loading the work.
Okay, makes sense. Fewer steps, but much harder steps.
Exactly. And this structure, alpha plus beta k, leads to one of the most, I think, academically fascinating points in the paper. They show it looks just like a neural network.
A neural network? Seriously? Like for AI? How?
Well, think about it. Input, initial guess, output, final solution, 62K. The equation 62K plus beta looks exactly like a standard linear layer in a neural net. Output, weight input plus bias.
Ah, so alpha k is like the weight matrix and beta the bias vector?
Precisely.
Yeah.
They call it a shallow linear network if you just look input to output, or maybe a deep linear network if you consider the recursive steps to build the coefficients.
That's a wild connection. We've talked about physics-informed neural networks, PINs, before, like Racy, Perdicaris, and Karnidakis' work from 2019. They use physics in the training loss.
Yes, and that's the crucial difference here. With standard PINs, you set up a network, and then you train it using optimization, guided by the physics, to find the right weights and biases.
You tune it until it fits the equations and boundary conditions.
Exactly. But here, with this higher-order Jacobi, the physics, embedded in the matrix A, gives you an explicit training-free definition of the parameters. The math itself tells you what alpha k must be. No training needed.
Wait, so the physics is the network. The math defines the weights and biases directly.
That's the key insight. It's not just a resemblance, it's a derivation. This gives, as they say, deeper insight into PNNs, which are often treated as black boxes. Here, the parameters aren't mysterious numbers found by optimization. They come straight from the problem's mathematical structure.
And it completely bypasses the whole training process, which can be really time-consuming and computationally expensive for complex PNs.
Exactly. The physics provides the interpretability and eliminates the training cost. It's a really powerful academic point, showing how these structures can emerge directly from classical methods.
That feels significant.
Yeah.
Building a neural network-like structure where everything is transparent and derived from first principles.
It's a very strong bridge between these two worlds.
Okay, mine's slightly blown there.
Yeah.
And speaking of surprising results, the paper also says this method can directly compute the inverse of the matrix.
Yeah.
How does an iterative method give you a direct inverse?
Yeah, that sounds counterintuitive, doesn't it? But it comes straight from that main equation. Alpha k, alpha plus beta. What if you start with the simplest possible guess? $6, $1, the zero vector.
Then the first term, alpha k x0, just disappears. You're left with 6 0.
Right. And remember, beta k is built up recursively. If you fully expand that recursive definition all the way back to the start, the expression for the section data, which is converging to the true solution, section 1 being real, becomes this product of matrices involving the lower order alphas, all multiplied by the initial beta, which is batting male.
Wow.
So essentially 6 egos text product matrices. Comparing this to 6 and 1 being well, you can see that the product of matrices must be the inverse, and 1, 1. They give the explicit formula, and 1, pot k plus a guy.
So, by setting the initial guess to 0, the bias term beta k, through its recursive construction, effectively computes the inverse matrix.
That's what falls out mathematically. And the significance beyond just finding the inverse is that it formally proves the equivalence of direct and iterative methods for solving the system, provided the iterative method converges. It shows that this structured iterative process is performing the necessary steps to arrive at the same result as direct inversion. It's a neat theoretical link.
That is a powerful theoretical statement. Okay, so we have this method. Fewer iterations, looks like an interpretable AI network can even find the inverse. But we keep coming back to the cost of calculating those alpha coefficients via matrix multiplies. What about real-world problems where the matrix aisle isn't fixed? Like in nonlinear physics where APDAL depends on the solution $6, or adaptive meshes where LA changes.
Right, if out keeps changing, recalculating those alpha terms or the inverse every single time would just kill performance. That upfront cost becomes a constant burden.
So how do they deal with a dynamic dollar?
They introduce something called the induced source iterative scheme. The idea is clever. Solve the new system with the changed matrix, let's call it $1, without recalculating the expensive coefficients or the inverse for Italy. Instead, you use the inverse you already calculated for the original baseline matrix.
Use the old inverse to solve the new problem.
You rewrite the new equation, x is b dollar, as xx equals b plus a day. See that extra term, say that extra term, a day x. They call that the induced source, b da.
So the original matrix equation what's data x equals b plus bi is equivalent to the new one, or c dot x equals b.
Exactly. The scheme then iterates. In each step k, you estimate the solution using the known inverse of the original matrix A tox A1 B plus bi k, where D tox Paydars is the current guess for the induced source.
Okay.
Then, using the 6k, you figure out what the new dynamic matrix AK would be. It might depend on 6k. You calculate the mismatch or residual based on the difference and use that to update your estimate of the induced source, B dollars, for the next iteration.
So you're ping-ponging. Use the old inverse with the current induced source to get a new sextalar, use that sexall to find the new matrix AJA and update the induced source. Repeat.
That's the essence. You keep adjusting B dollars until 6all neuralers are consistent with the current A dollars. And the crucial part computationally is that the main work inside this loop is applying A1, which you can do efficiently using the higher order structure or other means if A is sparse, and doing matrix vector multiplications like AAD.
Much cheaper than the matrix multiplications needed to recalculate alpha k or a new inverse from scratch every time L changes slightly.
Exactly. You pay the big cost once up front for the baseline L1 or its higher order equivalent, then handle variations relatively cheaply.
And they also connect this induced source scheme to neural nets.
They do. They note that this iterative process, especially when alpha-gal depends on $6 through some function gamma, naturally assumes the form of a deep recurrent neural network. The iteration, updating an internal state, $sim, mirrors how RNNs work. It suggests why recurrence is needed in networks tackling dynamic or nonlinear systems.
So even the adaptation mechanism maps onto an AI architecture. The connections keep stacking up.
It really reinforces their central theme.
Okay, let's talk brass tacks. Performance. The paper has computational complexity analysis, O notation, and actual timings.
Right. Complexity, using big O notation like in Table 2, just tells you how the work scales as the problem sizing grows. Standard dense matrix multiplication or direct solves are often around ON3, maybe ON2.376 with fancy algorithms. Iterative methods can sometimes do better, maybe ON2 or even ON, on special matrices with methods like multigrid.
And their method's coefficient generation step.
That initial expensive part, generating alpha k, has the same computational complexity as matrix multiplication. So its scaling follows whatever matrix multiplication algorithm you use.
Okay, potentially costly scaling.
Yeah.
What did their actual tests show in Table 1? They used NumPy, SciPy, PyTorch on CPU and GPU?
Yeah, this is where you need to look closely. They compared the time to generate their coefficients against the time for built-in direct solvers in those libraries. Looking just at the scaling exponent, how fast the time grew with the coefficient generation often showed a better lower exponent, especially on the PyTorch GPU setup, around ON2.02, compared to the exponents measured for the built-in solvers they tested, which ranged in their tests from roughly ON 1.9 to ON 2.8.
So the rate of increase in time was size and looked better for their generation step. That's the algorithmic improvement they talk about.
That seems to be the point, yes. The underlying algorithm scaling seems favorable. However, if you look at the actual wall clock times in that table, for many matrix sizes tested, the total time for their method, generation plus solve, was often higher than just using the library's built-in solver.
Okay, hold on. Better scaling, but slower times. How does that work?
The key is that upfront cost combined with high parallelizability. Generating the coefficients is dominated by matrix multiplication, which is perfect for parallel hardware like GPUs. Their GPU results ON 2.02 scaling for generation demonstrate this.
So even if the constant factors or overhead make it slower for smaller and on less parallel hardware, the better scaling means that for truly massive problems, especially on hardware built for parallel linear algebra, like GPUs or maybe those photonic circuits they mentioned, its parallel nature should eventually win out. It will scale better to enormous sizes.
That's the argument. The potential for speedup lies in its suitability for massive parallelism on future hardware, tackling problems that are currently intractable.
Okay, that makes sense. So let's zoom out. What's the big picture here? What are the main takeaways from Goona and Tarsissi's work?
I think the biggest thing is this conceptual bridge. They've rigorously shown how a classical numerical method can be reformulated into something that is structurally a neural network, but crucially, one where the parameters are explicit, interpretable, and come directly from the physics, not from a black box training process.
So the benefits are transparency, interpretability, no training cost, and this potential for better algorithmic scaling on parallel hardware.
Exactly. It suggests a different path for physics-informed AI, not just using physics to guide training, but using physics to directly define the network. That could be huge for building trust in AI for science and engineering.
And they're planning to push this further.
Yes, the paper explicitly mentions extending it to nonlinear systems and time-dependent differential equations. That's where the really complex real-world action is. Applying this framework there could be game-changing. They also mention looking into AI techniques like pruning for matrix sparsity.
Right. So to wrap up this deep dive, we started with the core need to solve by-AX, XABBU, from physical simulations. We looked at classical Jacobi. Then we dove into this innovative higher-order Jacobi method from Goona and Tarsissi.
Which gives that exponential cut in iterations, but at the cost of heavy matrix multiplies up front. And we saw its surprising structure as an explicit, interpretable, training-free neural network.
We learned it can even directly compute the matrix inverse, connecting iterative and direct methods. And we saw the induced source scheme for handling changing systems, which also resembles a recurrent neural network.
And finally, we understood the performance picture. Maybe slower for moderate sizes now, but with better algorithmic scaling that promises significant advantages on massive problems using parallel hardware like GPUs.
It really does blur the lines, doesn't it, between classical numerical analysis and modern AI. So here's the thought to leave you with. If we can derive neural network structures and their parameters directly from physical laws and math, completely bypassing opaque training, what does that really mean for the future? Could we be looking at a new generation of AI for science that's inherently interpretable, efficient, and trustworthy, built directly from the principles we understand?
It's certainly a compelling direction, a potential future where AI in science is less black box, more derived principle. Definitely something to think about.